Okay, so we have a lot to cover today, so we're going to go all the way into the wee hours of 2 o'clock. I'm Gabe Frost. I'm a lead on the engineering team that builds all of the video and audio capabilities in the operating system across our family of devices, from codecs all the way up to the APIs that are available in the browser that are standardized W3C HTML5 APIs and into the Windows runtime. So I've been at Microsoft for about 10 years, about 15 years total in the industry, working on things from core networking, deep low-level streaming things, congestion control algorithms and things like that. And for the past several years, been focused on media. And so streaming applications are right in my wheelhouse. And I hope that we can share some information today that's useful for you all. So we're going to talk about building video and audio streaming apps. We're going to break apart what the anatomy of a streaming app is, the things that go into creating these radio-type apps where you'd stream audio over the internet or video streaming, whether that be on demand or live. And in particular, break apart the API options that you have available to you across our family of devices. If you're building store applications, there's a few to choose from, and we want to clarify why you would use one versus the other. And we're going to give a couple examples, more of a traditional video streaming app example, and another that is a custom style streaming app. Something that you might not have expected, so we'll see how it works out. And then we want to talk about some of the considerations for audio, in particular if you're building an app that you want to run more universally on the phone as well as on PCs and tablets. There are some distinctions that are worth pointing out. And then last, I'm going to outline some of the things that we've been hearing from customers, from you. And hopefully you'll come up afterwards and we'll spend some time talking about some of the feedback that you have, things that you'd like to see us focus on. But the things that I have listed at the end are a little bit of a hint to the types of things that we're digging into now, that we're thinking about, that we feel are important. So you reflecting on those and giving us feedback will be really important. So what is a streaming app? It generally is broken up into these categories. The first thing these apps tend to do is they acquire a manifest, which is an XML file or some sort of playlist file that describes where the video and audio streams are in order to be able to adapt, to get closed captions, to get ads, things of this sort. So having a file, for those of you who are familiar with smooth streaming, would have a good sense of what this means, or Apple's HLS or MPEG-Dash. There's a media presentation description that you download, your app parses, you can figure out where everything is so that you can get into the business of adapting the quality when necessary. In addition to closed captions, which can be within band, so in the stream, or it can be out of band, like, for example, a web VTT file or a time text markup language file that you'd pull down separately in time, showing captions with the video playback. There's also supporting multiple languages. All of these complexities go into building streaming apps, and we hope to offer the platform APIs that enable you to build those types of apps. Okay, so when looking at the API options, the most important ones to think about are the top three. These are the ones that are available in the Windows runtime across our family of devices, where you use the same programming model. The first is what's standardized in the W3C, something called media source extensions. We talked about this a lot during the last build conference. This is new to modern browsers, but enables plug-in free adaptive bitrate streaming inside of the browser and on Windows inside of web apps. The second is something called media source extensions. For those of you who are Silverlight developers in the audience, you'll be familiar with this because it's largely what's used by most Silverlight apps for doing any kind of video or audio playback. And the last is custom media foundation sources. This is the underlying platform that all of our media capabilities are built atop. And so getting down and writing Win32 native code is possible. It's the lowest common denominator, and it's available across our whole family of devices. Now, there's supplementary SDKs as well. One is Smooth Streaming, which many of you are probably familiar with, as well as Apple's HTTP live streaming. So we're not going to go into a lot of detail about either of these today. If you have questions specifically about HLS, here's an email address that you can send to, because there's various different options available depending on the type of device, whether it's a phone or PC or tablet or Xbox that you'd like to have your app support. Go ahead and send us an email and we can help direct you. If there's one thing that you walk away with today, it's this: convergence is a priority for us. And those top three that I mentioned, media source extensions, media stream source, and custom MF extensions, are converged and available across our family of devices. Any of the work that we do looking forward, as it relates to streaming or media playback, if it's exposed in the runtime, we treat convergence as a priority so you don't have a fractured ecosystem, so you can create those universal apps that play everywhere. Now, I mentioned a lot of different options, so let's get a sense of what that means for you in the context of complexity versus control. When you think about something very simple like progressive download, which really isn't streaming, it's really just about getting a file down into memory and playing it back. There isn't anything that you have to do. You set the source of a media element and it just downloads and plays. This is what we've traditionally seen on the web for a very long time. Smooth streaming is very similar to that in that you don't have to deal with the complexities of streaming inside of your app. Whereas a progressive download, you would specify the path to a file that you would download and play. With smooth streaming, you specify the path to a manifest file. And then the platform looks at all of the different options inside of that file, and all of the adaptive streaming happens for you. You get it largely for free. There's some knobs you can turn, but as an app developer, you don't have to do all of the complex work of fetching down MPEG-4 fragments and adapting bit rates and whatnot, like you have to do if you're using media source extensions in your HTML5 site or app, or media source extensions. These are the two that we're going to spend some time talking about today. In effect, your app has to deal with all of the complexities of streaming, adapting bitrate, inserting ads, all of these things. All the way to the other side of the spectrum is writing a custom MF source. If you don't have to, you really shouldn't. And we'll go into some detail about why that is the case. But it is the lowest common denominator. And if there's some fancy things, some very custom things that you want to do, you're able to. But as you can see, you have very little control on one side of the spectrum, but it's very simple. And on the other side of the spectrum, you have a great deal of control, but that comes with a lot of complexity. As they say, no good deed goes unpunished. So let's take a look at a more traditional video streaming app. So I mentioned we have this thing called media source extensions. It's something that is enabled in all modern browsers, or most modern browsers. It's a W3C standard. It's what we think about as a replacement for media plugins like Flash or Silverlight plugins in the browser. Netflix and YouTube are very popular apps that use this today. And it works with the video and the audio tag. There's extensions we refer to as EME, or encrypted media extensions, that allow these sites to work with DRM. In our case, that's PlayReady. Now, media source extensions, like the audio and the video tag, are built atop IMF Media Engine. So they're an abstraction away from Media Foundation, like all the other components that we have. And the difference here from the video tag or the audio tag is the app is responsible for retrieving all of the video and audio segments and pushing them into the media pipeline through this media source that you create. It takes fragmented MPEG-4 as input. And all of the samples that go down into the pipeline are the MP4 file format is parsed for you. You don't have to deal with any of that. The decoding is handled for you, offloaded into hardware, all the way up through rendering. So the app's responsibility is about getting the samples, adapting the bitrate, doing all of the complexities associated with streaming apps, and then the pipeline takes care of everything else for you. There's a reference player that Microsoft OpenTech contributes quite a bit to, as well as some industry players. It's available at the Dash Industry Forum, and it's a JavaScript file called dash.js. You can go download this. It's open source. I think it's up on Git. And you can get a sense of how all of this stuff works together for doing streaming. I must be projecting in the wrong mode. There it is. Our friend Big Buck Bunny again. So this is a site that's available. You can view the source of this site and get all the JavaScript if you like as well. That shows how media source extensions are used. In this case, as a demo, what we're showing is rather than adapting dynamically to the bitrate, what it looks like to adapt manually. And so we have this little bar down here where if we move the bitrate up, we would see the video automatically adapt to those conditions. There it goes, so that you can see the quality improve dramatically. So you can play around with this. OK, so let's deconstruct that. So creating a media source is pretty straightforward. The way that it works is you essentially new up a media source in your HTML5 app here. By the way, I want to set some context really quickly before I go into this. All of the code that I show you today, you can download these after the fact. And at the very end, in the resources of this presentation, there's links to all of the MSDN samples so that you can go and look through the code and use it yourself. So don't feel like you have to jot things down or take lots of pictures. You know, I wanted to make sure that you could like engage with me on this and not feel like you have to like really rush through writing things down. So the way that media sources work is you essentially create this media source, which is something that represents your content. You define a set of callbacks that you use to pump data into the media source and get notifications from it. And then you attach it to the video tag or to the audio tag, where then you play and fast forward and do all of the types of things you would normally do on the video tag. So it's just about decoupling the content as an adaptive source onto the video tag. And so this is just a very simple case. So you create the media element, you define some callback mechanisms to feed data into it, and you define your source buffers for audio and video that you're going to feed your segments into. Now, the key takeaway here is, or one thing that I want you to be clear about is, you use the playback timer tick. So you can register to say, hey, let me know whenever the playback timer goes forward. This is the clock that you use to monitor when you need to append segments into the media source. This is where you all throw tomatoes at me because there's no code. I tried and I tried to figure out the easiest way to describe something useful here about how you do the adaptive streaming. How many in the audience have actually written code that does adaptive bitrate streaming? Yeah, there's thousands of lines of code in order to do this, depending on how complicated you want to get. So this is where the magic happens, so they say. You can go take a look at dashif.org and go for free, grab this dash.js file, which describes all of the detail here. But the key thing is This is where your app does all of the work. This is where you monitor some quality signals. For example, you'll take a look at your buffer depth and make sure that you're not starving your buffer so that the video stops and shows the spinny donut. You monitor the quality of service, whether you have frame drops, things like that. You monitor the network conditions. And you use XML HTTP request, XHR, in order to go fetch segments, in order to put them into the media source buffers. So here's an example of I'm going to show you two signals that you can use to adapt the quality. One is looking at the network conditions. This is pretty straightforward. When you use XHR to download a media segment, you keep record of how big that segment is and how long it took you to actually download it when XHR completes. You keep a little journal of this, and you keep a sliding window, and you average that out and say, how much throughput am I actually getting? And compare that to the bit rate of the video that you're trying to download. If those don't match up, you should switch streams. The same is true for frame drop. So W3C defines an interface called Get Video Playback Quality. And this is off of the video element. And it tells you things about what's happening in the pipeline. It tells you how many frames that you have in the pipeline, how many of them were corrupted, how many of them were dropped. You could use this as a signal to what's happening with the CPU. You would expect to see these types of things happen if your CPU on the client was pegged. Or you'd expect to start to see corruption, for example, if the server CPU was pegged and it was trying to encode and ended up with encoding problems. So both network and frame drops are two quality signals that you can look at for adapting inside of your app. Now, ads. How to do ads using HTML5. The general guidance for this is to create two video tags and swap them out. So the idea is that you have your main movie playing, and you have some signal about when you should display an ad. And when that time comes, you pause your main video and hide the video element. You unhide the video element that you're using to display your ad, and you play it. And then when you want to switch back, you do the opposite. The downside is obviously you take more memory because you have to have them both at the same time. There's some challenges for doing ad insertion using media source extension, where you're just trying to append data from one type of video onto another. One of the problems is oftentimes ads are traditional MPEG-4 or some other format, not fragmented MPEG-4. And so when you do those types of source swaps, it can cause problems. So this is the way that you should be doing it until a better solution exists. We're working on that. This is true across all browsers out there today. But one thing to note here is that oftentimes we've experienced when we see an ad that at some point during the ad, you can skip past it. So here's a very simple example. Again, you use the playback timer. So as the ticks go on and you say, oh, OK, let's calculate really quickly when we're, let's say, 50% through the ad. So when you're 50% through the ad, you can unhide, and this is just a very simple use case examples, but you could unhide the controls, which allow the user to then seek. Before that, you would have the controls hidden so that they can't seek. Obviously, in your app, you would be a little bit more creative than that. But this is just a very simple example about how you go about doing that. Now, closed captions are something that's quite easy to do inside of your web app or your website. The browser supports natively two types of what we call out-of-band caption files. One is TTML, or time text markup language. Another is WebVTT. You can specify these files, essentially what they are, even though the format's different in each of them. They both accomplish the same thing, which is a set of timestamps and a set of text that you want to be timed with those timestamps. So you use the track element to specify what these, the path to these particular files, which would cause in the standard media controls, the closed caption control to light up. And when you choose the closed caption control, you see a drop down with the different languages that you choose. And when it's turned on, the standard control will wire up to the playback timer, and it will render that text that's in those files at the appropriate time. If you don't use the standard media controls, you can subscribe to an event to get called every time there's closed caption text that you could then compose onto the screen yourself. XAML apps have to do lots of hard lifting today for this, so we apologize for that. It's something that is in our what we've heard from you at the end. So let's take a look at a custom streaming app. Sort of video, sort of not video. But the way that you build custom streaming apps is using something called Media Stream Source. This is something we introduced in Windows 8.1 that Silverlight developers will be very familiar with because this has been around for some time. So we expressed this API in a WinRT form. So while your app won't port line for line, you'll be very familiar with it. It has functional parity with what's available in Silverlight. It works with both the XAML media element as well as the HTML5 audio and video tags. And just like the media source extension, it works with DRM, with PlayReady. This is something that Smooth Streaming has used to implement their end-to-end for a very long time. So media source extension is very similar to Media Stream Source in what its function is. The difference is that unlike MSE, which takes fragmented MPEG-4 as input, Media Stream Source takes elementary streams as input. The app, and actually before I move forward, in both compressed or uncompressed. We're going to be showing some fun things you can do with uncompressed samples in a second here. But the app, just like media source extensions in HTML5, is responsible for doing all the adaptive bitrate streaming itself. It also has to parse the file format, the custom file format. So you could use it to add custom format support to Windows. You can do custom streaming formats. You can do adaptive bitrate streaming. MSS is a toolbox that you can do all sorts of things with it. And just like all the other options, you don't have to worry about decoding and rendering. All of that stuff is done in the platform for you. So let's show a funky way to use the media stream source. So what I'm going to show is a custom C++ component that projects a WinRT API that allows a caller to ask for samples. Now, this custom component uses Direct3D to generate on the fly a 3D object. And so when a caller asks for samples, it's getting a 2D texture of those D3D samples that are uncompressed, and it shows them inside of the media element. So this is a MSDN sample. If you searched MSDN for media stream source, it would come up. And there's two options in here. One shows how to stream an MP3 file and play it back. And the new one that was just added shows how to use it with D3D. So all the code is available to you. What this is doing is just using D3D to generate a spinning cube on the fly. And the app uses MSS to just go grab samples from it and display it inside of the media element. This could be familiar to folks who've seen the Xbox avatar that's shown inside of the store apps out there. It actually uses something very similar in approach, except it does it using a custom IMF byte stream because media stream source was not available at the time. So let's get into it. So with media stream source, you can specify any type of audio or video, whereas media source extensions only takes fragmented MPEG-4. For video, it takes AAC, things of that nature for audio. But because it can take such a wide array of audio and video, you have to be explicit to tell the platform when you initialize the media source what the video or what the audio looks like. So there's various different encoding properties that you can choose from using the video encoding properties in the Windows runtime. And in this case, what we're doing is we're essentially saying we're going to create uncompressed video, or we're going to be able to source uncompressed video. That's 8 bits of red, green, blue, and alpha. And it's going to be 720p. We create a video stream descriptor that you use to initialize the media source when you create it. And an interesting note is that whenever you're switching streams in a more traditional case where you'd be streaming from the web, if, say, you want to switch to a lower resolution or a lower bit rate, or if you want to put an ad in place, it's really easy. All you have to do is just update the stream descriptor and then just start pumping that data into the buffer. So unlike HTML, where you'd rotate out the video tags with media source extension or media stream source, you can just use the existing buffers and just start passing the data in as soon as you update the stream descriptor. So this should look very similar to you. It's exactly like media source extensions in HTML5. You create a media source. In this case, we're setting the buffer time to be very low, 1/4 of a second, because it's like a real-time example where we want the cube samples to be passed down the pipeline very quickly. But in effect, you create the media source. You define some callbacks that you use to pump data into it. In this case, it's called sample requested. And then you attach the media source to the media element. Very simple. And then you control the media element the way that you always have. So appending data into the source buffers, again, this is where the magic happens in the sample requested. This is where you use sockets or you use HTTP client in order to go grab samples and monitor your quality signals and pump them into the source buffers. It's all very much the same. In this case, though, this is using that custom WinRT projection that I mentioned to get samples from this DirectX surface generator. OK. So the last of the 3 that are converged across our platform are custom MF extensions. So these are native C++ COM components that you write. And they're used for things like custom streaming, if you want to implement a custom format, if you want to implement an encoder or a decoder or some sort of video or audio processing component that acts on every sample that goes through it, you create custom MF components to do that. These components, it's just a DLL, you package up inside of your app, and it can only be used by your app. So even though it's a lower level C++ component that you would traditionally be able to use in Windows Media Player, we sandbox them so that they're only available inside of your app, because not everyone is as good at coding as you, and they cause problems. And it would be terrible if they inserted one of these things and it started to cause your app to crash. So we keep them all packaged up inside of one app. They're those things down in the red box. So they're custom sources, custom syncs, custom encoders, decoders, effects. We talked about media stream source. So in the context of this talk, we're talking about streaming. MSS is almost always a better option. If you think you need to write a custom byte stream, you should send me an email and convince me why you should have to do that. It's much easier to use a WinRT projection, which you can, if your reason is that you want to write C++, you can do that in WinRT as well, so please do. But there's 2 ways that you can use your custom IMF byte stream if you did want to write one of these. An example that we're going to show is smooth streaming. So the smooth streaming SDK that you can get on the MSDN gallery is an implementation of a custom IMF byte stream that has a WinRT projection that you use to feed the data in from your app. So if you want to build an SDK and you want that SDK to run everywhere, you should use MSS. But if for some reason you need to use a custom MF component, you could do it this way too. So there's 2 ways that you can get it to load. One is by registering it and associating it with a specific file extension and MIME type, so that if someone passes in to the media element source attribute a file with your custom MIME type or attribute, then your media component would get loaded, and we would pass all of the data down to your custom component. The other way is to register what we call a custom scheme handler. A scheme is the protocol part of a URI. So you could have my custom scheme : //. So in the source attribute, if you were to specify your custom scheme and then whatever data you want in the URI, that you would get that passed into your application. So what does it look like? First, you have this custom IMF byte stream. It's a DLL. You need to register that in your app manifest. These slides are different than the ones that I created. So we'll talk about the steps, and then hopefully the right slides will show up. So step 1, you register it in your app manifest. Step 2, you register the format with what we call the Media Extensibility Manager. So inside of your app, there's a WinRT API that you register it and say, hey, here's the DLL that I put in my app manifest. And step 3 is you set the source using your custom, whether it's a scheme handler or whether it was the MIME type or file extension to your media element. So here's what the manifest looks like. You essentially define an in-process server, and you specify the path to your DLL, which implements your custom IMF byte stream, and you specify the class as your entry point, essentially, inside of that DLL. To register it, you create a new plugin using the Media Extension Manager. And then you register your byte stream handler, which is the activatable class that you specified inside of your app manifest, as well as the particular file extension and MIME type that you want to associate it with. You could also call register scheme handler in order to register your custom scheme that your byte stream exposes. And last, you just use that particular file extension in the file that you specify in your source, and your component will load. Those were examples of how you load the IIS Smooth Streaming SDK for use inside of your app. So this is one we don't feel as good about, but it's important to talk about the distinctions. So phones, while they're all Windows 8.1, there is a distinction about how you do background audio on the phone compared with the PC and tablet cousin. The reason for that is that we didn't do as good a job as we should have. Lots of it is converged, other parts aren't. If you're looking at the future, use the version that I describe here for phones, because we will converge. Convergence is a priority. And over the several coming months, we'll be looking at making sure that that background audio model is converged everywhere, because there's benefits to it. So in addition to again, my slides are out of order, so now I'll speak to what's on the slides. While the background audio model isn't converged, the system media transport controls are converged. So you'd use the same code in order to specify what metadata shows up when you press the volume key and you see the shell show you a system set of buttons for controlling the media that's playing over the lock screen, for example. So the way that you publish the metadata, the way that you handle input from those buttons is all converged, and it's all the same across phone, PC, and tablet. This is what they look like on the tablet. Whether you say pause is enabled or play is enabled, the different buttons light up in the same way across phone and tablets. And here's just a quick example of what those look like. We talked about background audio not being entirely converged, so here's what that looks like. This is an app manifest. It looks the same generally across phone, PCs, and tablets. The difference is that on phone, you actually specify an entry point for a background audio task, which is different than a PC, where your audio, your app is prevented from being suspended so that it can play audio, which means that there's a whole bunch of things that are happening that otherwise don't need to be. On the phone, the benefit is that you essentially offload all of your audio playing capability, as well as the media transport controls and all that, into a background task that runs that's dedicated to just playing audio, so that the rest of your app can go away, and you get better battery life and better efficiency and whatnot in doing it this way. So that's the model that we're going to converge. What does that look like? So defining your background audio process is, you might notice that the namespace and the entry point, the class, are the two things that you specified in your app manifest. And so you just implement that class. It's pretty straightforward. The most important thing that you do in this is you handle all of your audio playback capability here, and you handle all of your media transport controls. If you don't, your app will get suspended, and then when you push the buttons on the media transport control, they go to dev null, and nothing happens, because now all of your audio code is running inside of this background process. The way that you communicate between your app that's in the foreground and your background audio process is just by passing messages. These messages are handled using key value pairs. You can define whatever you want in order to specify them back and forth. So getting transport commands, these are the buttons from your app. There's two ways that you can get transport control commands. One is the buttons that you have inside of your app. You may have built a set of custom controls, or you may be using the standard media controls that are available to you in the platform. So you want to be able to get messages from your app, but you also want to be able to get messages from those buttons that show up in the shell, the system media transport controls from the lock screen, for example, when your app isn't visible. So this is an example of how you do that from your app. So in effect, you can define whatever key value pair you want. Here I've shown start playback and pause playback, and your app sends those messages down. If your app's written in JavaScript code, for example, you would use a message passing mechanism that I'll show to send these commands down. And then your app takes the corresponding action in order to start the playlist or to move to the next track on the playlist. Getting transport controls from the system is the same as how you'd implement it across all of our devices. You essentially create a system media transport control, and you handle the arguments that are passed in specifically from the button press. And so whether or not it's a software button press, like you'd only see on a phone, or you're on a PC and you have hardware buttons, or, for example, you have a Bluetooth remote control, for example, all of those button presses are passed into the app in the same way. So you implement this once the first time, it's inside of your background process, and you'll be able to take complete control. Updating the metadata that's playing is exactly the same as you would do on any of our family of devices. So in this case, inside your background process, whenever a track changes or you want to update any metadata, you do that very simply by using the display updater off of your transport control object. And again, you pass these messages and key value pairs up to the app, so that your app knows to change its now playing UI. You might have album artwork or your playback ticker that's going on your screen. You need to make sure from your background process you're telling your app the state of what's happening. So here's some simple JavaScript code that shows how your app talks to the background player. So we just have a very simple audio, an audio tag, and you create a new background media player. Your background process won't start until you actually create this object. So make sure that you do that. If you're trying to pass messages to something that doesn't exist yet, you can imagine you'll run into some trouble. So make sure that you create that background media player first. And then this is just a very simple case where you have a file you want to play, and you pass the message down to your background audio player using a key value pair so that it knows to start the playlist, because all of your playback code is inside of your background process. And here's just a very simple case about how to actually get those messages outside of the background player up into the foreground process. So it's very simple. The key takeaway is you pass messages back and forth using key value pairs. All of your media transport controls should be handled inside of your background process, and all of the audio playback that you would do should happen inside of that background process. If you're a radio app, for example, like Pandora or something like that, all of the code would actually live for doing the streaming or getting ads. All that lives inside of the background process. So you just organize your code in that way. Even though the rest of the code that you would use is WinRT code, and it's the same across all of our devices, you organize it into a background process on phone, whereas you wouldn't do that in a PC until we converge it. OK, so we're listening. We've heard lots of feedback about things that are difficult. The first is that convergence is really important. We really get how painful it is when you want to write an app and that code isn't universal across all of our devices. And so we've spent a lot of time during this conference talking to you about universal apps and how important it is, and so we really get it. Anytime that we expose an API in WinRT, you can expect that that API will be converged across our devices. We're going to work really hard to make sure that that's the case. The other thing that we heard is that there's lots and lots of Apple's HLS content out there, and you want to be able to play it inside of your apps, and you've had to jump through lots of hoops in order to make that work on Windows. So we've heard that you would like to see HLS treated as a first-class citizen in WinRT to make it really easy. And streaming is really hard. That slide that has comments in it that says the magic happens here, we'd like to be able to just show you 10 lines of code that do everything for you. We started out by just exposing some very simple interfaces, whether you're using Media Stream Source or whether you're using Media Source extensions. There's so much app code. In order to do all of that adaptive bitrate, we want it to be more of a smooth streaming-like of experience where if you don't feel like that adaptive bitrate streaming is something that differentiates your app and you just want to get it for free, we'd like to be able to provide that. And we talked about media source extensions where the app handles all the file parsing and things like that you don't get with media source extensions, but MSE is not available to XAML apps. So we've heard that you'd like a WinRT projection of MSE so that if you're familiar using that interface, you could write a XAML app that could use it. Our closed caption support is largely focused on web apps because it's something that has existed more simply in the web for some time. Those of you who are familiar with Silverlight or writing XAML apps know that you've had to create your own custom controls. None of that nicety has existed other than using like player framework SDKs and things like that. So we want to make sure that you don't have to go use all of those various SDKs and that you can rely on the platform in order to get great player controls as well as closed caption support. And if you don't want to use standard controls in the system, you can build your own controls and have APIs in order to get caption information both in-band in the stream, which would be important for HLS content, but also out-of-band. And the last thing is that I'm sure most of you recognize this. Live content is something that's getting incredibly important. We saw a lot of it over the last 12 months with sports. The Super Bowl and Major League Baseball and basketball, sports as well as all types of other content like with reality TV and whatnot. Lots of services want to make this content available across multiple screens. And there's some challenges associated with doing live content as compared to on-demand content. Live content, oftentimes, you have to think about ads a little bit differently. Like there's standards for doing ad signaling and handling ad rotations and whatnot just tends to be a little bit different. And so we're thinking about that, and we've heard that you'd like for us to think about that to make sure that it's easy for you to build your apps going forward. So I promised you some resources. Here they are. You can download this after the session and click on these. But we have MSDN samples for a lot of things that we talked about here today, as well as a link to a session that I did last year, which talked about background audio, and it talked about media source extension or media stream source in a different, simpler way for audio. So we have lots of samples out there for you to take a look at. And that'll be it. Thanks. So I'm also quite happy to have you all gang up on me and answer lots. I can answer a lot of your questions, even if I don't see a clock in here how we're doing. But even if you want to go like find a couch or something and just talk about media for a while, I'll make sure that I dedicate my time for the rest of the day to help answer your questions. So I appreciate it. We really appreciate your feedback. So if you can go online and provide some feedback about the session, about your experience overall, about how terrible of a job I did, that would be really great. We use it to get better every year and make sure that we're providing you the right information. So again, thank you.